So as we were discussing, whenever you have sudden change in cross section, or if you want, you have points where the load is applied, concentrated forces applied, you might have in these points higher concentration levels. This is why after getting the value of sigma that in the way we do it usually, we should take into consideration multiplying this value by a certain factor, which is called the concentration stress factor K. And this factor is determined experimentally. So, for example, if you have, let's say, a certain particular geometry, you have the following section that is subjected to bending. Then what will happen is that you can say I have a critical zone. The critical zone is the one where I change from a large thickness to a relatively low one. So you can be sure that this part will be more stressed than the other part. And in particular, okay, at this change of, so here, the value of the radius of the fillet, if you want, will affect the stress concentration. So if you have if you want a straight angle, of course, the stress concentration will be much higher. So at these points here, you will have very large value of stress concentration, and K factor will be significantly high. So smoother is the transition, better will be, if you want, lower will be the stress concentration, and K will be reduced. This is why what we do in general, we do experimental work to determine by which factor the stress that is calculated according to the formula MC over I is multiplied by which value. Okay, so experimentally we can determine for each configuration of let's say ratio R over D and D over D. For this example, how K will vary. Okay, so here we performed like dimensionless analysis. These are pi groups. So we varied for, we did several experiments. We varied R over D and D over D, and we measured the maximum stress value, and we compared it to the conventional one calculated. This allowed us to determine what is the stress concentration factor K. We should multiply by the maximum stress we calculate according to MC over I using the experiments done. So as you can see here, for each combination of R over D and D over D, you can read. So if I tell you, for example, R over D is 0.15 and big D over small d is 1.2. So you can see here that this curve corresponds to, these curves are for different values of D over D. You can see that for 1.2, D over D equal 1.2 correspond to this curve. So the intersection point with R over D equal to 0.15 will give you the corresponding value of K. You can read it on the vertical axis. So it's nearly here 1.55. Now, as expected, larger is the fillet radius, larger is the ratio R over D, lower will be K, because the transition will be smoother, okay? And then the concentration, the stress concentration effect will be lowered, okay? However, whenever I have small values of R compared to D, I am closer to the straight change with the 90 degrees angles, which will cause very large concentration of stress at in these zones. Okay. Now, of course, if I change the geometry, I need to use another chart. So if I have, for example, this geometry here, which is different than this one, then I have also a critical region, which is here between. So I have first sudden contractions and sudden expansion. So this zone will be, of course, the most critical one. So first I conduct my analysis on this section, and then As the value of stress I get, I multiply by K, and K is again determined experimentally by using this chart, because after doing several experiments, we were able to summarize the results in a chart. So now we can directly use the chart. We just have to determine what are the main ratios. Of course, here also same ratios, small r over small d. R represents the radius of the fillet over D, which is the small thickness, if you want. And we have the ratio of big D over small d. And also, of course, larger is big D over small d, larger is K, because this is the same observation in both graphs, because the sudden variation will be steeper. Okay, so you will have a more aggressive, if you want, contraction and then expansion. This will cause a higher concentration of stress. Okay, so as expected, larger D over D, larger is K, and larger R over D, smoother transition. This allows us to reduce the value of K. Okay, now let us do some practice on reinforced concrete beams and on stress concentration. We have the following problem. A concrete beam is reinforced by 3 steel rods placed as shown in the figure. The modulus of elasticity is 20 gigapascal for the concrete and 200 gigapascal for the steel. Using an allowable stress of 9 megapascal for the concrete and 140 megapascal for the steel, determine the largest allowable positive bending moment in the beam. So this is quite similar to what we have seen before, except that whenever we have a concrete beam, we should know that concrete can only sustain compression, it cannot sustain tension. So the part above the neutral axis will be able to resist, but the one below it, of course, I'm talking if I have a positive bending moment, then the upper part is subjected to compression, the lower part is subjected to tension. Only the upper part will be able to resist because concrete can sustain compression but not tension. This is why in the lower part I should put steel rods to reinforce my concrete beam. Now, in case I put the bending moment in the opposite direction, then of course I have to add steel rods in the upper part, because I should add always steel rods in the part subjected to tension and not the one subjected to compression. Okay, here, since we are dealing with a positive bending moment, the upper part is compressed. So for the upper part, no need to do any change, because already concrete can sustain compression. However, because concrete is weak in tension, in order to not have rupture, we reinforce. This is what we call reinforcement. We reinforce concrete by using steel with it. And we consider that steel will support tension without, it will not rely on concrete. This is why when we draw the figure, we don't consider the concrete part below the neutral axis. As we mentioned before, we just consider that we have the rod, the three, in this problem, we have 3 steel rods. So we just have 3 steel rods, which will sustain the tensile effect. Now, in order to continue the analysis, we should determine the modified section. The modified section and the position of the neutral axis. So as we discussed before, whenever we have 2 different materials, we should find the modified section corresponding to having equivalent same materials in the figure. So this is why the first step will be to determine the coefficient N to modify the area of steel into an equivalent area of concrete. So you have N equal to ES over E concrete, which is 200 over 20 equals to 10. Now, since you have 3 steel rods and each steel rod has a cross section of pi d square over 4, then for 3 steel rods, the total cross section is 3 times pi d square over 4. And here you can keep your dimensions in millimeter, then you get your area in millimeters square. And don't forget to multiply by n to have the modified section. Now, as we mentioned before, we consider that the thickness of this equivalent area is negligible. So I just add an area of negligible thickness and large length, like this. I still need to determine, as we discussed before, the position of the neutral axis. And again, this position is determined based on the information that we know that the neutral axis should pass by the centroid of the modified section. So we can just apply the rule that sum of ai yi equal to y bar of the neutral axis times a. Now, since we considered the origin of our y-axis at the neutral axis, so y bar of the neutral axis will be 0. And then we can solve for sum of ai yi equals to 0, as we discussed in the course material. Let us apply it here in this problem. So we want to locate the neutral axis. It's somewhere below the top. We don't know this distance. We call it x. And then we apply the formula. We say the area of this part is 200 times x. And the centroid of this part is at x over 2 from the neutral axis, so times x over 2. Now this part is below the neutral axis, so minus NAS times this distance. And this distance is, to determine this distance, let us go back to the previous, to our figure. As you can see in the figure, you just take D to be the distance from the top level to the center of your steel rods. So these are your steel rods. The center line of your steel rods is at 50 millimeter from the bottom. So it's at 400 minus 50 from the top. So this distance is 400 minus 50 equals to 350 millimeter. Okay, and then you can say that I can express the distance from the steel area, the modified steel area to the neutral axis as d minus x, which is 350 minus x. So this distance is 350 minus x. This is the absolute value of y2, and you put minus because it's below the neutral axis. And now you will get a second degree equation function of x. If you solve it, you will get one positive value and the other root is negative. So the other root will be rejected. So you just consider the positive root, which is, you can verify that it's between 0 and 350. It's 150.72 millimeters. So we solve for x. Therefore, now we know the position of the neutral axis. Once we know the position of the neutral axis, we move to the step of finding the inertia of the modified cross-section about the neutral axis. Okay, so to get your inertia, you have two parts, part 1 and part 2. For part 1, it's a rectangular cross-section, and the neutral axis is at the edge of your rectangle. So you can directly apply, or you do the parallel axis theorem, or because for a rectangle, it's a known value. If you take the axis passing by one of the sides of the rectangle, then you can say automatically that the inertia about the neutral axis is equal to bh cubed over 3. Okay, and if you don't know this formula, it's fine. You can apply the parallel axis theorem, because if you do it, okay, you know that from parallel axis theorem, the inertia about an axis passing by the center of the rectangle is bh cubed over 12. And then, in order to find about the neutral axis, what should you do? You should apply the parallel axis theorem. So you should add plus area, and the area is b times h, times the distance from the axis passing by the centroid of the section to the neutral axis square. And this distance is h over 2. So when you do h over 2 square, you will get plus a times h square over 4. And already you are multiplying by bh, so it's like adding bh cube over 12 plus bh cube over 4, and 1 over 12 plus 1 over 4 is 1 over 3. So in general, whenever you have a rectangle and you want to find the inertia about an axis passing by one of its sides, no need to apply parallel axis theorem. You can directly use that the equivalent inertia about this axis is bh cube over 3. Okay, this is why here, if we apply it here, b is 200, h is x, and you calculated the value of x. So then for part 1, the inertia is 1 over 3 times 200 x cubed. Now, you should add the inertia of the second part, which is represented by the steel area, okay, modified by multiplying by n. Now, as we mentioned before, this thickness is negligible. And because the thickness is negligible, if you want to apply the parallel axis theorem, you say that I consider first an axis passing by the centroid of area 2. But because this area is of negligible thickness, its inertia with respect to an axis passing by its centroid is 0. Because what will make the inertia is to have a distance from the axis. If all points are on the axis, no inertia about this axis. And since we have negligible thickness, we can make this assumption that the inertia about this axis is 0, okay? Because all points can be considered on the same axis. And therefore, we just have to add the parallel axis theorem term, which is plus the area of 2 times the distance between the neutral axis and the axis of area of steel modified, which is, this distance is 350 minus x. So you just have to add plus a2 times 350 minus x square. And don't forget that a2 is the modified area, so it's n times as, a of steel. Okay, and then you can compute your total inertia. This is the total inertia of the modified section about the neutral axis. And since all the dimensions you are using are in millimeter, you will get the value of I in millimeter to the power 4. Now, just in the final step, make sure to do proper conversion of unit. If you want to assess now what is the maximum stress in concrete and what is the stress in steel, then you should convert your units. So we know that concrete is subjected to compression, and sigma compression in concrete, okay, is equal to the maximum value is at the top, will take place at the top. So at a distance of x from neutral axis, and n is 1, so I don't need to multiply by anything because my reference material is concrete. So I just say it's m times x over the inertia of the modified section. Okay, x value was already determined, but just pay attention for unit. In order, in this problem, okay, they gave you the value of the bending moment, and they want you to determine the value of no, here if you want, they want you to determine the maximum possible bending moment, a positive bending moment applied on the beam. So you should not exceed the allowable stresses. And they gave you what is the allowable stress for concrete. So of course this is a compression stress, and what is the allowable tensile stress for steel. So as usual, you find what is M maximum to not exceed 9 megapascal in concrete. What is M maximum to not exceed 140 megapascal in steel. And then between the two values, you select the smallest one because both conditions should be satisfied. You cannot satisfy one condition and keep the other not satisfied, you will have failure. So between the two values of M maximum you find, you select the smallest one. Okay, so this is a strategy starting with an allowable stress of 9 megapascal for concrete. Then by applying our formula, we can get M, because we know that sigma is provided, it's 9 megapascal. So here, in order to obtain your bending moment value in Newton meter, do conversion of units. So first use sigma in Pascal. So if it's provided in megapascal, you should multiply by 10 to the power 6 to convert it to Pascal. N is a coefficient, it's the ratio of, if you want for concrete, it's 1 because the reference material is concrete. Y is, as we discussed together, is X. It's the, because we are considering to find the maximum stress. The maximum stress will take place at the top level. So sigma max will correspond to Y equal to X. And we have I value was calculated in millimeter 4. You should provide it now in meter 4, so that your, and of course Y should be in meter, so that your bending moment value calculated will be in Newton meter. Okay, so M is equal to sigma I over N Y. Okay, and then we can replace for concrete, we have sigma is 9 megapascal, so 9 times 10 to the power 6. The inertia, to convert to meter 4, I just multiply by 10 minus 12. So I get 681 times 10 to the power minus 6. And I replace here over, because concrete is the reference material, N is 1 for concrete. And the distance Y here corresponds to the maximum distance from the neutral axis, because we are designing on the maximum allowable stress. Then it's equal to the distance X, which is already determined. Just don't forget to convert it to meter. So you divide by 0.15072. This will give you 40,664 Newton meter, or 40.7, here they missed the decimal point, 40.7 kilonewton meter. Okay, so now you got your bending moment for, that is the maximum allowable bending moment that can be applied to not exceed the maximum compression stress in concrete. So this is if you want a maximum 1. So first calculated value for the maximum bending moment. But it's not enough, because we cannot exceed the allowable compression stress in concrete, and also we cannot exceed the allowable tensile stress in steel. So the next step is to find what is the maximum value of the bending moment that can be applied to steel. So if I apply now this formula for steel, already they gave me that the allowable stress for steel is relatively larger. Okay, and you have 140 times 10 to the power 6 times. Now, concerning I, it's the inertia of the modified section, same value used before. So we just have to multiply by 10 minus 6 to convert. So 10 6 times 10 minus 12 will give 10 minus 6 to convert to meter 4. Over, now keep in mind that for steel, because you have a modified section, the stress value is multiplied by N. And this is why here, when you get sigma maximum allowable, it's NMY over I. So to get the maximum bending moment, you divide by N. You divide by N times Y. N is equal to 10 as calculated previously. And Y represent here, because we are designing based on the maximum tensile stress, is the distance from the neutral axis to the steel level. Here for steel, you just have one level because you are neglecting thickness. While for concrete, we always select the farthest point. Okay, so for steel, the distance from neutral axis to steel rods is 350 minus X. X is already calculated, so you can find the value of this distance in millimeter. And don't forget to convert it to meter in your equation. Then you get that the second maximum value for the bending moment is 47.8 kilonewton meter. And as usual, we should select the smallest between the two because the bending moment should be smaller than 40.7 and should be smaller than 47.8. The value that satisfies these two conditions is m equal smaller or equal to 40.7 kilonewton meter. So this is the maximum allowable positive bending moment that will not lead to failure in my structure. Another problem. In the following problem, we have a rectangular beam shown that is made of a plastic for which the value of the modulus of elasticity in tension is 1/2 of its value in compression. For a bending moment of 600 Newton meter, determine what is the maximum tensile stress in this beam and what is the maximum compressive stress. So first, as you can see in the figure, you have a positive bending moment applied on your cross section. This will lead to compression of the upper part and tension of the lower part. Now, I don't know where is my neutral axis, but I know in additional information concerning the properties of my beam is that the modulus of elasticity is not uniform because the modulus of elasticity in tension part is 1/2 times the modulus of elasticity in compression part. And therefore, this is equivalent to a beam with different materials, okay? And our purpose then first is to determine where is my neutral axis. So since I have two materials, because I have different elasticity modulus, okay? Here, if you want, I have the same material, okay? But this material will behave in a different way in tension and compression. In general, with the majority of materials we work with, we deal with one modulus of elasticity. It's not changing between tension and compression. This is why we were able to treat before, if we have one material, we considered that we treat it normally, we have a linear variation. Here, this material has specific properties. It behaves in a different, its elasticity is different in tension and compression. And this is why we can treat it as different materials. And we can consider that the part sustaining compression is different than the part sustaining tension. And then the methodology of thinking is equivalent to the one with different materials, okay? So the idea is first, we should determine where is the neutral axis position. And to determine the neutral axis position, we can do similar analysis that were done in reinforced beams. Because we say we don't know where is the neutral axis. Let us call the distance from the top of our beam to the neutral axis x, and then the height of the remaining part is the total height, which is 100 minus x. And then we can say, whenever we do this division, that since the upper part, since we have a positive bending moment here, the upper part is subjected to tension, and the lower part is subjected to the upper part to compression, the lower part to tension. And let us take the reference material. For example, you can select the reference material as you want. Here, they selected the reference material in the upper part. So we can say that for the upper part, n is 1 because this is the reference material, while n for part 2 is E2 over E1. Now, since part 2 is subjected to tension, because we have a positive bending moment, then E2 is E of tension, and E1 is E of compression. And according to the given, the modulus of elasticity in tension is half the modulus of elasticity in compression. So the ratio here is 1/2. And then to be able to proceed as we do, what should we do? We should modify the cross section. So we should multiply the area of part 2 by n, which is here 1/2. Yani here, instead of increasing the area, we should reduce it. So if you want, the modified section will be of this shape. We divide this width, the total width here, by 2, and we get a modified section of this form, like this. Okay, this is our modified section, and we want to determine where is my neutral axis. What is the value of x? So again, here we consider this is my neutral axis, and I consider the origin of y-axis on the neutral axis. So y bar should be 0, because we know that the centroid of the modified section should be on the neutral axis. And therefore, we apply that sum a yi equals to 0. And this is area 1, and this is area 2. Of course, area 2 after modification. Okay? So to start with, for area 1, and 1 is 1, because this is the reference material. The area is x times the width b, which is given here. It's 50 millimeter. So if we call this b, so for area 1, it's b times x, and the centroid is at x over 2 from the neutral axis, so times x over 2. Now for part 2, it's a rectangular part. Now, as we said, we use the modified area. The modified area is n2, which is half, times the initial width, which is 50, okay, times the height, which is h minus x, and times the distance between the centroid and the neutral axis, which is h minus x over 2. And we don't forget to put the minus here because we are below the neutral axis, equals to 0. This equation is a second degree equation in x. So as usual, we'll obtain one solution that is accepted and another that is rejected. Okay. So as we said, x should be, it's known to be, of course, between 0 and 100. So any value that is not in this interval will be rejected. So now you know the position of your neutral axis. Once you know the value of x, you can calculate now the inertia about the neutral axis for your system. So you say that the total value of I is inertia of part 1 plus inertia of part 2. Of course, for the modified section, so for this two section. And then, because you have two rectangles, you can directly use the formula of bh cubed over 3. Okay, so you can say that for part 1, the n1 is 1. So I just have that inertia is 1 over 3 bx cubed. However, for the second part, the width is modified. It's multiplied by n2, which is half. So n2 times b is the modified width, times 1 over 3 the height cube. The height is h minus x cube, h minus x, and we put it to the power 3 to have the inertia of part 2 about the neutral axis. And now, of course, we add these two values to get the total inertia of the modified section about the neutral axis. As usual, all dimensions here are in millimeter. Then we get the result in millimeter to the power 4. Don't forget to do the appropriate conversion. You can just multiply by 10 minus 12 to get the value in meter 4. And then you can use it to determine your maximum stresses. Now, the maximum stress in compression will take place at the farthest distance from the neutral axis, which is equal to x, and x was calculated to be 41.41 millimeter, just multiplied by 10 minus 3 to convert to meter. And the maximum tensile stress will take place at the bottom level at a distance of h minus x from the neutral axis. So now we are ready to apply our formula for sigma max. Sigma max in, and just pay attention here, because the lower part is modified, don't forget to multiply the stress you get by n. So for tensile stress, n is half. So tensile stress sigma is minus nmy over I. N is half. The bending moment applied here is given to be equal to 600 Newton meter. The value of y, as we discussed, is the distance from the neutral axis to the bottom level, and it's a negative because the tension is taking place below the neutral axis, since we have a positive bending moment, over the inertia of the modified section that we calculated together now. And then we can determine what is the maximum tensile stress to which my beam is subjected. Now, concerning the compressive stress, okay, to get the value of your compressive stress, also you say sigma equal minus nmy over I. Since compression takes place for the reference material n is 1, y is the distance from the neutral axis to the top level. I take the maximum distance because I'm designing, I want to find what is the maximum compressive stress to which is subjected my cross section of the beam. And then I have that I is the inertia of the modified cross section above the neutral axis, and m is given to be 600 Newton meter. By replacing these values, I get the value of my stress in Pascal. So of course, as expected, for the tensile stress, I get a positive value. For the compressive stress, I get a negative value. When you put the symbol sigma c, don't put the negative sign, okay? So whenever you have the subscript, this means that you know it's compression, then you just put the absolute value. So here, since you obtained 10 times a number times 10 to the power 6 Pascal, you can convert to megapascal. So in total, we have a maximum tensile stress of 6.15 megapascal and maximum compressive stress of 8.69 megapascal. Okay. And of course, to verify that we are on the safe side, these values should be compared to the maximum allowable tensile and compressive stress for this material. These two should be below the allowable values to not have rupture of our material. Let us practice now on concentration of stress. So we have in this figure two different geometries of beams, and we want to see how the geometry will affect the maximum stress. Okay, so we have for both cases a couple of moment m 2 kilonewton meter is to be applied to the end of a steel bar. Determine the maximum stress in the bar. If the bar is designed with grooves having semicircular portions of radius r equals to 10 millimeter, as shown in figure A, and if the bar is redesigned by removing the material to the left and right of the dashed lines, as shown in figure B. These are the two geometries we have seen in the charts. The charts we were able to draw from experiments, if you remember. And we said, depending on the ratios R over D and big D over D, we determine the concentration factor. So in such problem, first we say, what is the most critical section? The most critical section is the one of smallest area, which is this one. Okay, this part is more critical than other parts. And plus, of course, I just consider also this section will be also subjected to stress concentration because we have sudden reduction in size. Okay, so I will have stress concentrations at this level, and I want to determine then what is the maximum stress to which my section is submitted. First, I consider these are I have a rectangular section. I treat it normally as we used to do, but I should keep in mind that I have another factor, which is stress concentrations that will increase the value of calculated sigma. I should multiply the sigma by k, which is the factor determined experimentally, and I will find it now from the graphical chart, which is available for me. So to start with, we find for this cross section, which is my critical cross section, what is the inertia about the neutral axis, and what is the value of C, and then I apply my formula to get the maximum stress to which this section is subject. So first, let me characterize my problem. I have a rectangular cross section of length 100 millimeter, width 18 millimeter. Now, because I have stress concentration, because I have sudden change in cross section, I should determine the parameters needed to determine the coefficient K. And as you can see in this figure, both figures share same values. So for both figures, big D, so big D is the largest thickness. For both figures, it's 150. Small d is the smallest thickness, which is 100 for both. And r is the radius of the fillet or circle I have. So here, the radius given is equal to 10 millimeter. And also here, the radius is 10 millimeter. So I have comparable values, comparable ratios. But because I have different geometries, the value of k will change. And I will determine it from the graphs we have seen in the course material. So first I determine the ratios, and the ratios are equal here for both sections. Big D over small d is 150 over 100 equal to 1.5, and R over D is 10 over 100 equal to 0.1. Now I go to my charts and I use these numbers. So I write here D over D is 1.5 and R over D is equal to 0.1. Now, going to my graph, I say that first for the first geometry, so I have two geometries here, okay? This is geometry B in my problem, and this is geometry A, okay? So let me determine first for geometry A what's happening. I have big D over small d equal to 1.5. As you can see, this is 1.5. It corresponds to this curve. And I have that R over D is 0.1. It corresponds to this line. So the intersection is nearly at K equal to 0.2. While for geometry B, I have different section geometry. So I will look at the corresponding value of K for big D over small d equal 1.5. This is the curve of 1.5. And now I take the line of 0.1. I can see then that K is nearly 1.8. So here the stress concentration is lower because, as we said before, here you have sudden contraction followed by sudden expansion, while here you just have this difference once. Okay, so the concentration stress will be larger in this case compared to this one. Okay, so now once we determine the value of K, then we can continue the calculation normally. So we say that first, for inertia, for both sections, since we have same dimensions of sections and it's a rectangular section, okay, we said that B is 18 and H is 100 because look, if you look at your figure, okay, your bending moment is along this axis, okay? So this is your neutral axis. Your neutral axis is has the same direction of the moment vector. And then the height is 100 millimeter and the width is 18 millimeter for both cases. Okay, so when you do bh cube over 12, b is 18 and h is 100. Okay, so I is 18 times 100 cube over 12. This is in millimeter 4. And then you convert to meter 4 by multiplying by 10 minus 12. Now, of course, C, which corresponds to the maximum stress, is at half times the height, which is half times 100 equals to 50 millimeter. And now I can determine because here C is the same for both sides, the side subjected to compression and the side subjected to tension. So the maximum stress of tension is equal to the maximum stress of compression, equals to K mc over I. K factor is for stress concentration of stress. For geometry A, we have found that it's equal to 2.2 approximately, or 2.21 here. And then you just replace the bending moment value is given. It's 2 kilonewton meter. I convert to Newton meter in order to get sigma in Pascal. I use C in meter and I in meter 4. Then I get sigma in Pascal. And I can convert it, because I have times 10 6 Pascal, I can convert it to megapascal. And now the maximum stress for section B will be different. The only difference is in the stress concentration factor, because I'm applying same bending moment. I have same cross section, so same C, same I. So the only factor is the concentration stress. Since, as we discussed, and for geometry A is more critical, then you have more concentration stress and you have larger maximum stress observed compared to section B. Okay. So here the most critical section is section A, and it's subjected to a maximum stress of 147 megapascal. So we should pay attention to select an appropriate material that can sustain a maximum compression and the maximum tension above 147 megapascal for geometry A. And for geometry B, you should use a material able to sustain tension and compression above 119 megapascal. Now, one last idea in this chapter. We discussed several geometries of cross-section. I just want to tell you that sometimes they will refer to certain sections by just a name, and we can use tables to know the corresponding geometry. And you can find this in Appendix C of your book. Okay, so your reference book in Appendix C will give you the properties of different conventional shapes of beams. Okay. So for example, you can see here one possible geometry that is widely used is this one. This is called wide flange shape, okay, or W-shaped beam. So it's enough for them to tell you, for example, they can just say we have a beam W 760 times 257. And you are supposed to know its properties. Why? Because you have catalogs that will tell you for this name what are the properties. Now, the name means what? First, W will refer to the shape. Its W refers to wide flange shapes. Now, you have the other numbers, okay? So here, if you go to the bottom of your table, they tell you what is the significance of this name. So W will refer to wide flange shape. And you have that the first number will give you the nominal depth in millimeters, and the second number will give you the mass in kilograms per meter. Okay, so and value of nominal depth, when we say nominal, it's a way to characterize the section. It's not exactly, if you want, the the value of the right depth of your system. Okay, so here if you go to this table, you will actually know what is the real depth. Okay, so as you can see, the nominal depth will just give you an idea about the range. So when they say W920 times 449, then this is the nominal depth. You will have a range of values of depths that are around 920. So for example, W920 times 449 will be characterized by a depth of 4947 and an area that is given here in millimeters square. You can also, if you want, read here as different geometrical aspects. So what is the width? This you have here the depth, the width, and the thickness. You have several geometrical parameters characterizing this thickness, this cross section of beam. Sorry. So you have, for example, in order to determine this geometry, you should know what is the value of width BF, what is the value of depth D, what is the value of the thickness here of these parts. You have you have this thickness and this thickness also. All of these will be provided for you in the appendix, in the table, and also they give you also inertia, the coefficient as characterizing the section that we introduced together in this chapter. Okay, and you have inertia provided about x-axis and about y-axis. So all you have to do is to come to this whenever you see this name or the name in this form. You can just come to this table and read the corresponding values. Okay, so this is just a way to characterize beams by giving just their names, and the name represents, it has a certain presentation as we said. The letter is will refer to the shape. The first number is like a nominal depth, which will give you a range of closed depths. So for example, as you can see here, W410 will refer to depths between nearly 399 and 419. Okay, so it will give you an idea about the range we are considering. And as we said, the second number represents the mass in kilogram per meter. So sometimes if you need to have a lightweight, you can try to select lower values for the second number, etc. Okay, now we have several possible shapes of beams. Okay, for example, here we are still with W shape. You have all of these numbers are standard available numbers for our beams of this shape. Another possibility is S-shape beam. So it will be a little bit different in geometry, and it's characterized also by different geometrical parameters as the thickness here, the depth D, also the width B here, okay, and the thickness at this level. So same concept, okay, but it's a different geometry than the previous one. S shapes refer to American standard shapes of beams. And you can see here that you are having same way of presentation. You have the letter S to refer for the shape. You have also the first number will refer to the nominal depth. So as you can see, and you have that the second one will give you the mass per. So as we discussed before, it will give you an idea about the corresponding weight per unit length, okay, or mass per unit length. And then depending on the name I give you, you can search for the characteristics. So you can read all characteristics, including different geometrical factors and inertia about X and Y using the table. Okay. So we have mainly W, S, and also C shapes. So for C shapes, as the name indicates, it's in the form, the beam cross section is in the form of letter C. And also we use, if you want, same way of naming, and you have the letter C first to refer for the shape. You have the nominal depth, and you have the mass per unit length. Okay, so this is the designation way is similar in all cases. And then whenever I give you this name, you can find all properties. You can find the geometrical properties, and you can find the inertia about different axes of interest. Okay, so this is in brief how we can use this appendix. So we'll use it to know the properties of a section, knowing just its name. To do a small practice on this, we'll solve this problem. So you have the following beam. This beam is a W200 times 31.3 rolled steel beam that is subjected to a couple M of moment 45 kilonewton meter. So as you can see, they didn't give you any dimension for your beam in general. When they give you a cross section, they give you all dimensions. Why? To allow you to find the neutral axis position, to allow you to calculate the inertia. Here, they didn't do this because they gave you just the name of the beam. So you can go to the catalog. From the catalog, you can determine the inertia you desire. You need the inertia about this neutral axis, because the bending moment is parallel to Z. So you need to find from the table, from the appendix, what is the inertia about this axis for this beam, and that's it. Okay, so you know that the modulus of elasticity of the material is 200 gigapascal. The Poisson ratio is 0.29. You want to determine what is the radius of curvature of this beam, and what is the radius of curvature rho prime of a transverse cross section. So if you remember, at the beginning of the course material, we said that when the beam is subjected to a bending moment, you will have a certain bend formation. So you have a due to bending effect, you have this deformation that will lead to a radius of curvature in the bend section rho. And we learned how to relate rho to the moment applied. And we also said that we don't have only a radius of curvature in this bend section, but also in the transverse section. And we found a relation between, if you remember, the radius of curvature of the bend section and the transverse section. And we said that if this part will undergo tension, this part here will undergo compression. And as you can see, then you will have a radius of curvatures from opposite sides. So here, for the bend section, it's at the upper level. For the transverse section, is at the lower level. And we can relate the radius of curvatures through, as we have seen before, using the Poisson ratio. Okay, so what we will do now, first step will be to go to Appendix C and see what is the inertia about this axis for our beam. Then we'll use our formula for rho and for rho prime. Okay, so we have W 200 times 31.3. So let us go to our appendix to search for the properties of this beam. So first we will search, of course, in W shapes, which constitute the first tables. So let's go back to the first table. Okay, so we have W 200. So the nominal depth is 200. So let us search for it. As you can see here, as you move down, you have that so here, sorry, you have, okay, W. So first 900, 840, as we go down. Look here, if it's not present in this table, they should give you an additional table. Okay, so always, sometimes here maybe we don't have the continuation of this one, but we should always provide you with a standard shape that you have here the continuation in this part. So it's continued W shapes. Let us go down. So we have, as you can see, it's 200. Yes, that's it. So here you have W200. Now we have W200 times 31.3. So the second number is 31.3. So this is the line we are searching for. Okay. And which value will select among all of these values? Okay. We have to go here to know what we want. We just want the inertia about this axis. This is all what we care for from this table. Okay, so this is the corresponding axis. Okay, and we want to get the inertia about this axis here. So we need Ix, and this corresponds to this column here. Okay, so again, I will move down to my beam. It's W231.3. I'm here. Okay, I'm here. This is the value I want. Okay, which is equal to 31.3. And for the unit, they will tell you I'm using which unit here. I'm using the unit of 10 to the power 6 millimeter four. Okay, so I know then that the inertia of this beam in this problem is 31.3 times 10 to the power 6 millimeter 4. And then I can continue my problem. I go back to my problem. I say I know the inertia from the table. Now I will apply the formula for the radius of curvature. If you remember, the bend radius of curvature is obtained by 1 over rho is equal to m over ei, where m represents the value of the bending moment applied. In order to obtain rho in meter, we should put m in Newton meter, Newton times meter. E is the modulus of elasticity, should be in Pascal. So since they provided you E in gigapascal, you should multiply by 10 to the power 9. The inertia, don't forget to convert it to meter 4 by just multiplying by 10 minus 12. So you get 31.3 times 10 minus 6 meter 4. And then you can calculate 1 over rho. And then you do the inverse to get the radius of curvature of your bend section. Now, to get the transverse radius of curvature, as we demonstrated in the course material, 1 over rho prime is equal to the Poisson ratio over rho. So this equation, this relation between the two radii of curvature will allow you to get what is the radius of curvature of the transverse section. So we are done with chapter 4.